So now we know what features a list has that other collections don't. We've had a look at its different methods. We've worked through building a shipment class using those list methods. What about their different implementations? I briefly touched in Module 2 on the fact that each type of collection, each interface, has multiple implementing classes. And in fact, you can implement your own list implementations if you want. But in this module, I'm going to cover two key implementations which are shipped in the Java standard library, an array list and a linked list. Now, there are in fact other collections that implement list in the standard library, and they're dealing with concurrent collections. But this course isn't going to talk about concurrent collections, just collections which are used in a single-threaded context. But array list and linked list are two very, very commonly used collections. I'd say array list is easily the most popular and most commonly used collection of them all. And let's have a look at their different implementations and see when you might want to use one and when you might want to use the other. Because the key motivation for understanding these different implementations is they have different performance characteristics. An array list, on the one hand, is an array that's backed by a list. So if you've got index 0 in your array list being a door, that means index 0 in the list that backs it is a door. And the same with if 1 in your array list is a panel, index 1 in the array list is also a panel. And this has several important things to bear in mind. It means that because arrays are fixed size, when you hit the end of your list and you try and add yet another element, it needs to resize the backing array. Now, in order to avoid you resizing the backing array every time you add an element to the list, because that resize operation is computationally expensive, the array list doubles the size of that backing array when it runs out of storage. So if your initial size was, say, 2, you'd add the first element, then you add a second element, and when you added a third element, it would jump in size to 4. And when you tried to add a fifth element, it would jump to 8. When you tried to add a ninth element, it would jump to 16. So you can see that it means that resizing is less frequent as your list grows, which is quite nice. Array lists are a great general purpose implementation. If you don't know what the characteristics of your lists are, I would say just use an array list. It's kind of the default choice there. And it's a very optimized class and a very efficient class. It's also a more CPU cache sympathetic. So what that means is that modern CPUs have a great deal of difficulty given that they're so much faster than memory is in modern hardware. And in order to overcome the difference in speed between the CPU and the memory, they have a cache that sits between the two. And because array lists stride through an array, which is linearly laid out in memory, they're much more sympathetic to your CPU cache because that striding behavior is predictable. Now, if that doesn't make any sense, don't worry. It's a very, very advanced topic, and I'm not going to go into much detail on it. But just remember, array lists are very, very fast out of the box. The other choice that we have is to use a linked list. Now, a linked list in Java is a doubly linked list, and that means that each element in the linked list has a pointer to its next element and a pointer to its previous element. And the linked list itself keeps a reference to the head and the tail of this linked list. Each node within the list has a pointer to the element that's stored there and, as I say, to the next or the previous element in the list. So we can see here that our head node is a door, and it points to the next element, the middle element in our linked list, and that points to a panel, and that middle element points to our tail, and that tail element is a window, and the same back to the head. So you can see that as you're looping through your linked list, you're having to continually jump these pointers to find the next element in the list. Now, This is really, really good if you want to repeatedly add and remove elements in your list, because all you have to do is break that link of pointers and add a new element in. Whereas, for example, if you want to add a new element in the middle of an array list, we'd have to copy over all the elements to shuffle them up by one. So that's something this doesn't have. On the other hand, it is slower to iterate over because you have to keep on doing this pointer chasing all the time. I would say linked lists would not be my default choice of collection for a list, but you should use a linked list when you're adding elements at the start very frequently, because it's very, very cheap and efficient to do. Not so much with an array list, because as I say, you have to shuffle everything up. The other thing to bear in mind is that if you often use a list and index into a random point in the middle of the list, to do that with a linked list, you have to jump through those pointers n times until you get to your position in the middle of the list. And that means it's a lot more expensive to say, get the 5th element of a list or something with a linked list than it is with an array list, because you have to jump 5 times to chase those pointers. Whereas with an array list, you just dereference the 5th element in the array. Now I'm going to look at a performance comparison between an array list and a linked list. Now, if you're doing performance comparisons on your production code, you should think in terms of how your production code works. You should profile your production code, you should benchmark and measure your production code. I'm just going to talk about some general hints and pointers as to which of these two will perform better for different types of operation. And I'm going to do that in terms of asymptotic notation. Now what that means is big O. Big O notation is indicative of how the operation scales with the size of the list in this case. So if I mean it's order 1, I mean the size is constant. If you have a list with 1,000,000 elements in, getting the 100th will be just as fast as if you have a list with 1,000 in. That's nice and simple. Whereas if you say something like order n, it means it grows linearly with the size of the list. So the bigger your list gets, the more expensive that operation will be to perform. And the only other thing I will say is there's also a little omega on the add method. And omega means the amortized cost. And I'll cover that when I get to it. So if we want to get an element at a specified index, that's a constant time, an order 1 operation with an array list, because we just dereference that element from the array. Nice and simple. With a linked list, it's order n, because we have to jump through the linked list to get to that index. And the worst case we can think of is that we have to jump n times through the linked list to get to the nth element. Very bad. When it comes to adding things, the situation's reversed. An array list's worst case is that they have to resize the entire list and copy all the elements over. And that's an n-sized operation. The worst case is order n. Whereas with a linked list, you can just pop the element in. Nice and simple. You add at the end of a list, so you just take the tail element, add a new node in, add the element in, and migrate over your tail pointer. Nice and simple. However, array lists in practice aren't that bad for the adding. As I say, most of the time you don't need to resize the list. And because it doubles in size when it gets to the end, when it's a full list, you don't even need to resize that often. As your list gets bigger, the resizes become less and less frequent because it doubles in size every time. So, on average, when we amortize these costs, it's actually pretty constant, which is why I say it's omega 1, or on average, it's pretty constant. The contains operation in both an array list and a linked list is order n, because in both cases, the worst case scenario for finding an element is you have to iterate right to the end of the list, and it's the last element in the list. In each case, when you want to move on to the next element in your iterator, it's order 1, because In the case of the array list, you're incrementing the index number, and in the case of the linked list, you're saying, move the pointer up to the next node. Finally, there's the remove operation, and in the case of an array list, this is order n, because the worst case is that you remove the head node from the list, and you have to shuffle n elements down by 1. And in a linked list, this is order 1, because if you remove an element, you can just update the pointers to point to the previous element in the list, or if it's the head node, make the head pointer point to it. Nice and simple. So those are the different trade-offs. If you add, iterate, and get a lot, I'd use an array list. If you remove and add at arbitrary indexes, I'd think about using a linked list. But in both cases, benchmark, performance test before you make that choice, if it's important to you.